In this video, we're going to look at Hess's law using reaction equations. So we're going to look at how we can use the mechanism of a reaction to understand the enthalpy changes for those reactions. The first thing we need to understand when we're looking at Hess's law is that enthalpy is a state function. What that means is that enthalpy is completely path independent. So it does not matter how a reaction occurs, only where it starts and where it ends up. So we're going to examine a fairly straightforward reaction, and we're going to look at what happens if the reaction occurs in one step versus two, and the corresponding overall enthalpy. So we're going to look at the combustion of methane. So I'm going to write the one-step reaction here. So we have methane gas plus 2 oxygens forming carbon dioxide. And we're going to assume this is taking place in a closed system, so we'll have 2 liquid waters forming. And our enthalpy change for this reaction is going to be negative 890 kilojoules. So I'm going to draw that on our little potential energy diagram here. So I'll start with my reactants. So I have methane and 2 oxygens. And then I'll draw my products, which are carbon dioxide and 2 liquid water. And so we can connect those, and for now we'll just use this simple straight line to connect our reactants and products. And we see it's a downhill line, which makes sense because this is an exothermic reaction. And so we're going to have an enthalpy change of negative 890 kilojoules. This reaction can also take place in 2 steps. I'm going to write those 2 steps here. So our first step is going to be methane gas reacting with 1.5 oxygens to produce carbon monoxide, 2 liquid waters, and then that carbon monoxide is going to react with 1/2 an oxygen to produce carbon dioxide. The enthalpy change for our first step is negative 607 kilojoules. And the enthalpy change for our second step is negative 283 kilojoules. So I'm going to draw those here, but I'm going to first add together these reactions. So anything that appears on both sides of the arrow, so in both the reactants and the products, can be canceled. So I can cancel carbon monoxide, and I can sum together common molecules like oxygen. So my overall reaction here is going to be methane plus 2 oxygens to form carbon dioxide and 2 liquid waters. So we're going to draw this now. So we have the same starting reactants overall. In our first step, we're going to form carbon monoxide and water. So I'm going to draw that here. So carbon monoxide and water. And then we're going to add another 1/2 an oxygen here. And we will form our carbon dioxide. And so our enthalpy change for our first reaction is negative 607 kilojoules, and our enthalpy change for our second reaction is negative 283 kilojoules. If we add those 2 enthalpy changes together, we get the same enthalpy change as if the reaction occurred in one step. Because the reaction starts with the same products and same reactants and same products, it doesn't matter if it occurred in one step or in two steps. So in the last example, we were given reactions that added together very easily, but often we'll be able to piece together our overall reaction by having intermediate steps that may or may not add directly, and we may have to manipulate. So we're going to look at this overall reaction here. So we have carbon disulfide combusting with 3 oxygens to form carbon dioxide and 2 sulfur dioxides. And we're going to have 3 intermediate or stepwise reactions. So our first stepwise reaction is going to be the formation of CO2. So carbon plus oxygen forms CO2. And that has an enthalpy. So these enthalpy changes are often, you can often look them up in a book, which is why we use reactions like this. So we have 395 kilojoules. Our second reaction is going to be the formation of sulfur dioxide. So sulfur plus 2 oxygens forms sulfur dioxide. And that's going to have an enthalpy change of negative 296.8 kilojoules. And our third reaction is going to be the formation of carbon disulfide. So carbon plus 2 sulfurs forms carbon disulfide liquid with an enthalpy change of positive 87.9 kilojoules. Okay, so we have our 3 stepwise reactions, and we're going to ask ourselves 2 questions. The first question we're going to ask is the chemical species on the right side of the equation to match the target? And the second question we're going to ask is, does the coefficient in front of the chemical species match the target reaction? So if our answer to the first question is no, then we're going to have to flip our stepwise reaction. If the answer to that question is yes, then we won't flip. If the answer to the first question is no, to the second question is no, we're going to multiply our entire reaction so that they match. If the answer is yes, then we don't multiply. So we're going to walk through this question, looking at each species individually and asking those 2 questions until we're able to build this target reaction from these intermediate reactions. So we're going to start by looking at carbon disulfide. And I'm going to just highlight where each of these species is in my target reactions. So oxygen is kind of all over the place. Carbon dioxide is found in reaction 1. And sulfur dioxide is found in reaction 2. Okay, so I've highlighted where I've found my reactions. I want to start by looking at a chemical species that is only in one of the stepwise reactions. So carbon disulfide would be a good option, carbon dioxide, or sulfur dioxide. Oxygen would be a hard one to start with because it's found in 2 different reactions, and so it's going to be complex. So we're going to start just left to right. We're going to start with carbon disulfide, and we're going to go about asking those questions. So the first question is is it on the right side of the equation? So in our target reaction, carbon disulfide is a reactant. In reaction 3, it's a product. So it is not on the right side of the equation. So we have to flip reaction 3 in order to make them match. So I'm going to rewrite reaction 3 flipped. So I have my carbon disulfide, and I'm going to write that in blue so it matches my overall reaction, so that I can kind of keep track of when I've isolated a compound. And I'm going to create from that a carbon and 2 sulfurs. When I flip this reaction, I'm also going to change the sign on the enthalpy. So it was positive 87.9, now it's negative 87.9 kilojoules. So I've isolated and matched up my first chemical species. Next up, I'm going to do carbon dioxide. So I'm going to look at reaction 1, and I'm going to ask, is it on the right side of the equation? So here it's a reactant, here it's a product, here it's a product. So it is on the correct side of the equation. The coefficient here is 1, the coefficient here is 1. So I don't have to do anything to reaction 1 to make it match. So I'm going to copy it exactly as it looks. So I have my carbon, have oxygen, and I'm forming carbon dioxide. And because I haven't changed anything about my reaction, I don't have to change anything about my delta H value, so I'll keep it at negative 393.5 kilojoules. I'm going to skip over oxygen again and work on sulfur dioxide. So sulfur dioxide, found or shown here, is found in equation 2. And if we look, we are asking, is it on the right side of the equation? So product, product, yes. Are the coefficients the same? So we have 1 here and 2 here. So they're not. We need to multiply reaction 2 by 2. So I'm going to take reaction 2, I'm going to multiply it by 2. So that means that I'll be producing 2 sulfur dioxides and I'll have 2 oxygens. So I'm going to write that in green because oxygen is in my overall equation, and 2 sulfurs. All right, and since I've multiplied my reaction by 2, I'm also going to multiply my enthalpy by 2. So 296.8 times 2 is negative 593.6 kilojoules. So now I'm going to add these equations up, but I want to verify that I've actually canceled out. Anything that's in white is not part of my overall reaction. So everything in white should cancel. So I have 2 sulfurs on the reactant side, 2 sulfurs on the product side. I have 1 carbon on the product side, 1 carbon on the reactant side. And so my overall reaction cancels out to give me exactly what I want in my target reaction. So I'm going to add these reactions together. So carbon disulfide plus 3 oxygen, so 2 plus 1 is 3, forms carbon dioxide plus 2 sulfur dioxides. And my overall enthalpy change is going to be the sum. So I'm going to add together all of the enthalpies listed here. So 593.6 plus 393.5 plus 87.5, all negative. And I'm going to get an overall enthalpy change for this combustion reaction of negative 1,075 kilojoules. The next example we're going to look at is the combustion of liquid acetone. So we have acetone plus 4 oxygens forms 3 CO2s and 3 gaseous waters. And we're going to find the enthalpy of this reaction. So we have 4 stepwise reactions. We have the formation of acetone from its elements. We have the formation of carbon dioxide from its elements, the formation of liquid water from its elements, and the transformation of liquid water into water vapor. So we're going to go through the same process as last time, and we're going to start by highlighting each of our chemical species in the stepwise reactions. So acetone, we're going to highlight with red, is only found in reaction 1. Oxygen, we'll highlight with blue, is found in multiple reactions, making it a little bit tricky. Carbon dioxide, which we'll highlight in green, is only found in reaction 2. And water vapor, which we'll highlight in yellow, is only found in reaction 4. So we're going to avoid oxygen, but we're going to be able to match up the rest. So we're going to start with acetone. So first question, is it on the right side of the equation? No. So acetone is a product in reaction 1, a reactant in our overall reaction. So we need to flip this equation. Second question, does it have the right coefficient? So we have 1 in front of each, so we just need to flip it. So we're going to do that now, and I'm going to write all my acetones in red so that we've indicated we've isolated acetone. So this will be the decomposition of acetone into its elements. So carbon, hydrogen, and 1/2 oxygen. All right, and that's going to have an enthalpy change of positive 285 because we're going to flip the sign. All right, next up, we're going to look at carbon dioxide. So carbon dioxide is found in reaction 2. Same two questions. Is it on the correct side of the equation? So product here, yes. Does it have the right coefficient? It's 1 versus 3. So that's not correct. So we're going to need to multiply this second equation by 3. So that means that we'll have 3 carbons plus 3 oxygens to form 3 carbon dioxides. And because we multiplied the equation by 3, we also have to multiply the enthalpy by 3. And we get negative 1182 kilojoules. All right, so we have matched up carbon dioxide. So now we're going to work with water vapor. And so we need to look at equation 4, and for water vapor, we need to be a product, which it is, and we need it to be have a coefficient of 3, which it doesn't yet. So we're going to multiply this equation by 3. And so we'll rewrite this equation now, and we'll have 3 liquid waters forming 3 water vapors. And we're also going to multiply our enthalpy change by 3. So 44 times 3 gives us 132 kilojoules. Okay, so we have everything but oxygens. However, we haven't used up one of our equations. So we're going to start just canceling what we have here just to double check how things are going. So our 3 carbons can cancel. And if we look here, we still have some other species that are not quite ready to cancel. So this half oxygen can cancel, and that will give us here 2.5 or 5/2 oxygens. But we haven't been able to cancel our hydrogens or our liquid water yet. And so we're going to use equation 3 for that. And so in equation 3, we need to get rid of 3 liquid waters because they don't appear in our overall reaction. And so we're going to take equation 3 and we're going to multiply it by 3. Because liquid water is a reactant here, we want to keep it a product here so that it will cancel out. So we're going to take this equation and we're going to multiply it by 3. And so our reaction will be 3 liquid waters, 3 half oxygens, and 3 hydrogens. And our enthalpy, again, we're going to multiply our enthalpy by 3. So 285.8 times 3 is negative 857.4 kilojoules. Okay, so we can go back to crossing things out now. So our liquid waters, now we can cancel. As well, we can cancel our hydrogens. For oxygens, we have 5/2 and 3/2. So we have 2.5 plus 1.5, which overall equals 4. So we're going to sum together. So I'm just going to circle those in blue since we have the correct amount. And we're going to add together our reactions now to get our overall reaction and our overall enthalpy. So our reactions, we will have 1 acetone plus 4 oxygens, forming 3 carbon dioxides and 3 gaseous water. And our overall enthalpy for this reaction is going to be the sum of those individual enthalpies. So 285 plus negative 1182 plus 132 plus negative 857.4. And we get a total of negative 1,622.4 kilojoules as our reaction enthalpy.